Okay, now I got a little bogged down in calculations, and I should have made a better selection of the vectors that I started with. But hopefully that gives you a picture of the Graham-Schmidt process. If you look again at some of the problems you're asked, well, you're asked for the coordinate matrix of a vector relative to an orthonormal basis. Okay? Don't have a lot of clear board space here. I'm going to use this one. So to show you why the orthonormal basis is such a wonderful thing, this board's kind of wiggly, so my numbers are not coming out very clear. But this is U2, and this is U2, this is U3, and this is U3. Okay? Okay, let this basis be designated by big old fancy script B. So V relative to the basis B equals V dot U1, V dot U2, V dot U3 in a column. These are the components of V with respect to your orthonormal basis. A picture is you've got U1, U2, U3. This is orthogonal to this is orthogonal to this, and this is orthogonal to this. Three mutually orthogonal vectors. And looking at this from some perspective, you know, tilt it and stuff, so it looks like this. These are orthogonal unit vectors. And now we've got some vector v and if v is projected onto u1, you get this component. V projected onto u2, you get a component here. u3, v projected onto u2 gives you a component down here. Just like the components of a vector relative to x, y, and z, this is going to have component equal to this projection, but this projection is just v dot u1. So the projection onto u1 of v is and when I say projection, I don't mean the vector projection, I mean the scalar projection. It's v dot u1 over magnitude of u1. Now that's the picture we've drawn repeatedly, so hopefully you understand that. So we have v dot u1 over magnitude of u1, but u1 is a unit vector, so that's just v dot u1. So now down here you have I started to write the vector projection. I can still do that. What I wrote was true, but what I really want to do is go ahead with the vector projection. Okay, vector projection of v onto u1 is the scalar projection multiplied by the unit vector in the direction of u1. But the magnitude of u1 is 1, so this is just v dot u1 multiplied by u1. Now that gives you the projection down here of v onto the vector u1. Well, you can do the same thing projecting v onto u2. You're going to get this vector, and then you project v onto u3. Maybe you get this vector. This vector plus this vector plus this vector equals v. This vector is v dot u1 times u1, because this vector was u1 before I put the arrow through the label. This vector will be v dot u2 times u2, and this vector is v dot u3 times u3. So we've established that this projection, this vector projection of v onto u1 is v dot u1 multiplied by u1. this vector is v dot u2 times u2 this vector here is v dot u3 times u3. V is the sum of these three vectors, and that's what I wrote here. So all I'm doing down here is showing you why this is. And if V is this multiple of U1 plus this multiple of U2 plus this multiple of U3, then in terms of the basis U1, U2, U3, this vector is this column vector, because that's what this column vector means. Okay, so this, well, that's it. Of course, you have to understand representation of a vector in terms of a basis and so forth, which we've done previously. So this kind of builds on most of what we've learned up to this point. So it's a little bit challenging to grasp everything, but you just got to beat your head against the wall until you do. Okay, I really don't have too much more to say about it. It's an extremely powerful picture, as we'll see as we go through more of the course. So, Gram-Schmidt process allows you to take any basis, take an orthonormal basis, and if you have an orthonormal basis, your representation of the vector relative to that basis is very simple. These are easy dot products to do, just a dot product with a unit vector.